There you are. You're on.
Satisfaction here with the thing. Okay. So we like to keep it 45 to 50 minutes talk Q&A, and then we just if there is any questions, we can have time, but we're trying to keep it at the latest 4:45. 4:45, so that people can. People will invariably come and talk to the speakers who are really interested. So I'll give you some time for that, and then you can. All right?
All right.
Great.
You are going to do it?
Yeah. Do you have the tone? I took it off. Oh, yeah. All right. Good afternoon, everyone. Our speaker today is Joleth Mckenty. Now, I introduced him earlier today as a real engineer, meaning that he's actually licensed by the state of Maine to call himself an engineer, which is something that I haven't achieved yet. Jarlath was also a classmate of mine some long time ago, and he's here to talk to us today about technical innovation in a regulated world, how to do something new in a world full of rules. A little synopsis of Jarlath's career. I don't speak too well today. He's the Vice President of Engineering for ORPC and the Chief Technology Officer for the same company. He drives the development of the company's proprietary hydrokinetics energy technology. He earned his Bachelor of Science in Engineering at University College of Dublin in Ireland in 1986, and his Master of Science at Dartmouth College in 1989. And he comes to ORPC after spending more than 25 years in engineering and project management, having developed technical expertise in tidal power turbines, combined heat and power system, Stirling engines and refrigeration systems, control systems design, analysis, micromechanical structure, and marine engineering systems. Please welcome our speaker.
So first of all, it's really a real pleasure to be... What about it? Turn it off. Class. Okay.
We're getting there.
Should be on, yes. The little green light is on.
All right. Sorry about that, everybody. It was my screw up. Hopefully we'll work now.
So this is on? Doesn't sound like it. Oh, okay. All right. Okay, well, after that lovely introduction from Alex, thank you, Alex. As I was saying, it's really a pleasure to be back here again, and I really appreciate the opportunity and thank Alex and everybody else for making this possible. It's been a long time since I've been in Hanover, and I think it's fair to say that the school has changed a little bit since I was here. It seems a little bit bigger. People seem a little younger. Everybody else stays the same. As Alex was saying, I'm involved. I'm the chief engineer, chief technology officer, vice president for engineering for a company that's based in Portland, Maine. And we develop hydrokinetic turbines and hydrokinetic projects. And I want to talk to you today about technology development of a new novel technology with a lot of its own complexities and how to actually bring that out into the real world, into a highly regulated and permitted environment that we've created for ourselves here in the United States. A little bit about the project that I want to talk about. This is a little image of a town called Eastport, which is the easternmost city of the United States. There's a town called Lubeck across the harbor, which is the easternmost town in the United States. So there's a healthy rivalry between these two peninsulas. They're separated by about a mile of water, and it takes about 45 minutes to drive from one to the other. So that brings up the main expression of you can't get there from here. Eastport is right on the border of Canada, and in fact the big island that you see behind you there is Deer Island in New Brunswick. And it's a relatively small community, about 2,000 people, but it's got some interesting things. Because it's the easternmost town in the United States, the easternmost city in the United States, it has a very important cargo pier. There's a deep water cargo pier, which is ice-free year-round. That is the shortest shipping route to Europe. And from that pier, a new business has generated over the last couple of years of shipping live cattle to Turkey. The cattle are impregnated before being loaded onto the ships, so by the time they get to Turkey, you got two for the price of one. The other thing is these little round black dots that you see there, and that's, if anybody eats farm-raised Atlantic salmon, that's where that comes from. This is a major aquaculture area. As sea warming, as global temperatures are increasing and the sea is warming, that aquaculture business is actually suffering a lot. Eastport in general and that whole area of Maine is actually very economically depressed and has been since really the turn of the last century, since the 1900s. There are very, very large tides in Eastport, and there's a historic connection between one of the islands, the island of Campobello, and Franklin Delano Roosevelt. In the 20s and 30s, before electrification happened in the United States, there were two main hydropower projects that were under consideration in the U.S. The first of them was the Quati Dam Project, which FDR is looking at a model of here. The model still exists in Eastport if you want to go see it. The gentleman to the right is the project superintendent, and I met his daughter, who is about 80 or 85, at Kendall Retirement Community last night. She grew up in Eastport during this project. And this was a public works project that was funded as job relief. The other main project, the main electrification project that was happening at the same time was the Tennessee Valley Authority. Now, one of these you hear about and one of them you don't. The TVA got the funding from Congress to continue the work, and the Quati Dam Project had its funding cut. The reason for citing our project in Eastport and the Quati Dam Project in the same area has got to do with the tides. And I'm going to talk a little bit about what creates the tides, but this is sort of a bathymetric map of the Gulf of Maine. The deep blue shows the deep sections, the light blue shows the shallower sections, and you can see we got a sort of an isometric view up to the Bay of Fundy. And round about the Cape Cod area, we really don't have very much in the way of tide height, and as you work your way down east, down that coast, the tidal ranges increase quite dramatically. So about midway up the coast where Eastport is, you'll have a tidal range of about 20 feet in a normal tide. And as you make your way up to that prong up at the top there at the head of Nova Scotia in Minas Passage, we'll have tidal heights in the range of 40 feet on a daily basis. So there's a lot of energy here, and the question is, why is that happening in this kind of geometry? And if you think about it, out of seaward of the Georges Bank, this shallow area here where fishing happens, we've got tidal constituents, tidal forcing functions actuating on the ocean. And they're creating a tidal resonance in that bay. So basically it's simply a big bathtub where the tides are sloshing in and out. And as you go further up into the channel, that amplitude of oscillation is increased. So to model the tidal effects and to understand where the tides are going to be the strongest and where people should site a tidal energy project, a typical approach is to use a shallow water circulation model, something like this. This model is actually something that Dan Lynch was working on 25 years ago as part of the Princeton Ocean model. And it's a very small world. You meet these same people and professors who are doing the same work, working for the same groups over the last 20 years. So this finite difference model, this mesh, was actually created at the University of Maine, and its main purpose was actually to track the dispersion of lobster larvae up and down the coast. But we took the model results and started looking at the tidal speed results from that model. You can barely make out a little square there in slight gray, and that's highlighting the peninsula of Eastport. To the left-hand side of the peninsula, as you're looking at it, is Cobscook Bay. And you can see that leads into a series of embayments of different sizes. Very important ecological area in Maine. A lot of tidewater shallows and flats. I've seen more bird activity at various places up there than I have any place else on the East Coast. The other side of the island of Eastport is Head Harbor Passage, and that's one of the main shipping routes up into Canada. There is a very large tanker traffic through that channel up into Canada. On both sides of the peninsula are actually the areas where ORPC is interested in developing projects because that's where we have strong water flows. The other places in the world where you get very strong tidal responses from the local geometry are in northern Scotland in the Pentland Firth area, and in places like Cook Inlet, which is a very long bay in Alaska leading up to Anchorage. I think it's about 40 miles long and 20, 25 miles wide. I know a little bit more about Cook Inlet than I do about the Pentland Firth because we have a project site in Cook Inlet. And one of the interesting things about the tides in Cook Inlet is they are very large, but there's also a very significant phase shift from one end of the inlet to the other. So there's about a 3-hour delay in the tide from one end of the inlet to the other. Today's tides in Eastport, I've got a chart on the top, and it shows approximately a 20-foot tide today, and it's about 4 p.m. So we're at probably the 16-foot tide stage right now. And the chart below it is from the Minas Passage further up, and you can see the tidal range there is 3 to 14 meters in a day. So it's approximately 11 meters, 33 feet in one day. So that's an example of the increase in tides as you move further up the bay. I want to talk a little bit about how these charts are developed. Basically you go to Google, you type in tide chart for Eastport or Minas Basin, and it spits out this thing. This is a prediction of tide moving forward for the next 4 days. And in fact, I could run that prediction tool for the next 100 years, and I will have very good agreement with the actual tidal heights versus this prediction. And the reason is that tides are an astronomic phenomena. They are created by the motion of the moon and the sun. And those things we know very, very well. As a result, tides are very, very predictable. And as a result of that, if we generate energy from tides, that energy production is very predictable. I want to contrast that with wind, where wind is sort of a statistical, stochastic process, where you get a gust, you may get a storm next week, you may get no wind for a week. It's sort of a very intermittent resource. Tides are very predictable and pretty much always there. In terms of the United States, and I want to preface this by saying that the U.S. is actually not the world leader in tidal resource. We've got good tides in Maine, we've got good tides in Alaska and Puget Sound in Washington, but other places, they're a little on the weak side. What we do have is wave resources off the West Coast. We've got very significant wave potential in the Oregon and Washington and Northern Californian coasts. And between the two marine renewable technologies, wave and tidal, we're estimating that we could potentially serve 7 to 10% of the U.S. national electric consumption. That's a pretty significant new renewable energy resource that no one's actually taken advantage of. And, as we look to the future, that may be, we hope, a reality that we want to deliver on. Europe has a much higher potential. I don't actually have the numbers, but if you look at places like the Pentland Firth, north coast, the coast of Normandy, various other places near the North Sea, you have some extremely strong tides. The other thing that's interesting when you look at developing power from the oceans is that the human population is moving towards the coasts. Right now in the U.S., or right in the world actually, 70% of the world's population lives within 200 miles of the coast. And that's actually increasing. People gravitate towards the coast. Take a look at a night map of the United States and you see blinding lights on the east and west coast and a lot of dark spaces in between, other than maybe Chicago. The other big and new technology that's being developed right now is offshore floating wind. We have onshore wind. We have shallow offshore wind, which is basically onshore wind technologies just implemented in shallow areas. So basically monopile structures driven to the sea floor, driven through the sea floor. As you go further out, you get much more predictable wind resource and much stronger wind resource. And to take advantage of that, we're going to have to move to floating wind structures. And there's quite a few projects in the U.S. now developing those technologies. The Norwegians and Japanese, I've got to say, are probably technically far in advance of anything that the U.S. have done. Norwegian companies have deployed several floating offshore wind structures, as have several Japanese companies. But these technologies are all very similar. They start bringing up the questions of how you do design in the marine environment, how do you transmit electricity back to shore, how do you do your operations and maintenance, how do you do your deployment and retrievals, and how do you permit and license these technologies, and how you sell the electricity. All very similar questions, all very similar answers. So we've got a huge resource, and as I pointed out, some of that resource in a place like Cook Inlet actually takes time to develop from one end to the other. So you could talk about baseload generation using something like a Cook Inlet project. And it appears to be environmentally friendly. I'll talk about that a little bit. We do a lot of environmental monitoring. But all we have right now are the environmental results at a small scale. We got one unit in here, we got one unit in there. We can't detect any environmental response. What happens when you scale that up? If I put 1,000 units in, what happens then? That's a different question. And then another advantage that we talked about earlier on today is the fact that it's out of sight. Frankly, a lot of people don't like wind turbines because they don't like them in their backyard. They don't like the ideas of renewable energy technologies because you have to look at them. What they're really not seeing is the carbon dioxide in the air and the acid rain that we don't have as much anymore. We don't see the global temperatures warming. We pay a price for the energy we use. Sometimes you don't realize that. You don't see the nitrous oxide that you breathe. But putting these devices out of sight, either offshore or underwater, is actually a very positive thing from the public perspective. But right now in the U.S., the energy market has changed considerably over the last couple of years due to the low price of natural gas due to fracking. And that really puts a dent in the economics of all renewable energy projects, wind, solar, hydro even. So it makes it a very difficult economic environment to be in right now. And we've got to wonder how fracking will affect energy prices in the future. So ORPC was established in 2004. The general idea was that we were going to develop projects. We were going to buy technology from someone else. And, we saw all these wonderful pictures from European companies about these wonderful tidal turbines that they were developing, and then we go talk to them about buying them, and you found that you couldn't buy them. They didn't really exist. They weren't tested. So we started developing technology of our own. We went through a technology selection process and came upon the particular arrangement that we have, which I'll talk about in a minute. And over the years, as we developed this technology and as we developed the project in Eastport, Maine, we've become somewhat of leaders in the U.S. in terms of permitting these projects and how to get them licensed. We've developed relationships with the regulatory agencies, with the communities, and a lot of other stakeholders. And that's actually been a very valuable thing for us as a company. We have very, very good public acceptance of our technology in the state of Maine, very good PR, frankly, and people want us to actually come to their communities and help them install these kind of technologies. We've got three different types of technologies. I'm going to talk mainly about this TIGEN unit here on the right. But we also have a river system that's actually going to go on test in Alaska next year. And then longer term, we're talking about doing a floating system. The floating system would be in deep water situations, several thousand feet possibly. So we'd look at something like the Florida Current which is a pretty sustained unidirectional flow off the coast of Florida. All the technologies, they're all similar. They're all cross-flow turbine technologies. So this is sort of like an underwater windmill of a different type than you've seen before. They're all direct drive machines. There are no gearboxes involved. We took a decision earlier on that we wanted to minimize the mechanical complexity. And they're right now all permanent magnet generators, which generate DC power, which is transmitted to shore. I talk a little bit about the differences in these different hydrokinetic turbine technologies and maybe give you a feeling for why we chose one type over another. In the late 70s and early 80s, in the wind industry, there was quite a lot of work going on in what are called axial flow machines. This is a cross-section of an axial flow turbine, which is basically your standard three-bladed wind turbine that you see everywhere now. It is the technology that won out in the wind industry for good reasons. It's efficient, it's relatively low cost to build, and it's reliable. The other technology that was being developed at that same time was a cross-flow technology, which is the technology that we chose. And the initial test results from the cross-flow testing that happened was that this technology wasn't as reliable as the axial flow machine. There was a lot of early-stage failures in cross-flow turbine technology. Many of them out in the Altamont Pass in California. I don't know if anybody's driven through areas of Southern California where suddenly you come to a valley with towers and towers and towers of windmills, various designs. It was really a test center for various wind turbine designs in the 70s and 80s. But there's certain things about this turbine that we actually like from a marine environment, and it's preferable to us to follow this technology route rather than the axial flow machine. And these cross-flow turbines are actually beginning to see a resurgence in the wind industry as well, particularly in the small-scale domestic wind turbine business, and also actually in offshore floating wind. There's a couple of advantages that they offer in the floating wind market. I want you to think about this a little bit. This is a section through our turbine, and the arrow represents the rotational direction of the turbine. So you can see that top foil is kind of advancing into a flow that comes to the right. Okay, so we've got tides. Tides come and tides go, right? So this is a flow coming out of a channel. The turbine is rotating anti-clockwise here. What happens when the tide goes in the other direction? Does it stay with the same rotational direction or not? A little bit of a geometry problem. If you take that picture and just rotate it 180 degrees, it looks exactly like it did in the previous slide. So with cross-flow turbines, there's actually no need to change the yaw direction of the turbine. Irrespective of the direction that the flow comes at the turbine, it'll rotate in the same direction. This is a big advantage when you're trying to minimize the amount of mechanical structure and systems on a turbine. So if you think again to your onshore wind turbine, it actually has to rotate into the wind. With a cross-flow vertical turbine, it doesn't have to do that. It just sits there and accepts wind from all directions. Just to give you a sense of a little bit more perspective of what the turbine actually looks like, this is a unit in the at the manufacturers. The particular design that we're using has a helical sweep to the blades, and that helps even out the torque fluctuations that would normally happen with a straight-bladed turbine. Brendan's here, but if you want to look at Dr. Brendan Epps' models, you can get a sense of some of the torque variations that happen in a 2D model. And the problem with this complicated helical 3D shape is that it is somewhat of a bear to do any kind of analysis on. It is a geometry problem that befuddles me after 5 years. The top picture I couldn't get an animation of, but it's a 2D cross-sectional slice. It's just showing you some velocity intensities around the turbine. And the bottom section here is a 3D animation, a 3D simulation of the same thing, velocities through the turbine. Typically what you get from the turbine as a function of rotational angle is a torque curve that looks something like that. So it's a kind of a peaky behavior. As the blade is rotating around, there's a nice angle of attack at which everything good happens and you get a good lift force, and as it rotates into the downstream section, you lose all that lift and that associated torque. The electrical generation, let me go back to the CFD stuff for a minute because some people might be interested in it, and it sort of gets back to the work that Dr. Brendan Epps is doing here. CFD, computational fluid dynamics, when I was doing my work for you, we were using Fluent, and Fluent back then wouldn't allow people to have any kind of curvilinear boundary. It was basically block structures in 2D. And the code was written in Fortran, and I got to look at the code at the time, and it was, even I thought it was pretty ugly code. Fluent today is now a world leader in computational fluid dynamics based over in Lebanon, West Lebanon. And the ability to do these kind of 3D or these high-resolution 2D models is only something that's really come on in the last 2 to 5 years. And the things that are driving this are interesting because our CFD guy, the guys who produced this, is actually the guy who designed the lifting hydrofoil for the Team New Zealand America's Cup boats. And there's a lot of high-end boat racing design work going on that's really pushing these CFD tools forward. The major area of research is still sort of not quite right for cross-flow turbines. And makes me think that there are problems other places in CFD are all the turbulence models that fit into these the CFD codes. Need to be quite a lot of work done, I think, on those. The electrical generation, as I mentioned, we have a direct drive generator, so basically all 4 of our turbines in that TIGEN unit are on one shaft. They rotate the shaft. We've got a permanent magnet generator. The voltage is proportional to RPM, so we've got a variable AC output from that generator. We can't connect that to the grid. So what we do is we locally rectify that to DC, transmit it to shore as DC, and then rectify it locally as AC and feed it into the grid. There's an image of our system. You can see the 4 turbines, the common drive line. All that yellow upper structure sits on a bottom frame, that yellow lower structure, that is our foundation frame for the unit. One of the reasons for doing DC transmission, as you look at offshore wind projects, you actually see people talking about doing high voltage DC transmission for multi-megawatt units 25 miles offshore. One reason to do that is that there is DC transmission can be very efficient, especially when you do it at high voltage. But the reason that we're primarily interested in DC transmission is that we have multiple units in an array out in a bay. We want to be able to connect those units together and transmit that power back to shore in a single cable. And we also want each one of those units to be able to operate independently, to be able to operate at a separate RPM. We don't want to synchronize them. So DC offers a nice ability to do that. It's basically like connecting batteries together. I just want to go through briefly some of the technology development. 2004, 2005, you got to start small. You don't have any money, and you got to do things on a little bit rough. So we made our first turbines out of wood, steamed in a steam box and made by some ship's carpenter up in Eastport and covered in epoxy. And it worked. But part of the other problem about doing testing in Eastport in the winter is that you get kind of cold. So this is a typical day after a rainstorm the night before. So the first day's work is to go chip the ice off the test vessel. We had an admiral from the Navy. Never have an admiral from the Navy as a technical advisor. They always, his attitude was, you have no creature comforts. You can't have any walls on the vessel. You'll get blown around by the wind. No coffee, no pizza. He never showed up for the testing. So we improved the test systems a little bit. We got a little smarter and decided to do the test work in the summer when the days are longer and it's a little bit warmer. We built a nice deployment vessel, which we actually just transferred ownership of to Maine Maritime Academy last week. We built our new set of turbines. You can barely see them in behind the framework. And we started doing some testing, again, in the middle of the summer. Very nice. This is an example of a turbine under test underneath that test vessel. The turbine is vertically underneath that test vessel. It's trimmed out nicely. I want you to look at the angle of laying over of that mooring can. That gives you some sense of the water speed that's the drag loads that are acting on that whole structure. It's pretty impressive to be sitting out there with 6-knot flows. One of the issues about tides is even though they're very predictable, they actually don't happen the same time every day, so there's a time shift over time. So if you want to do a 24-hour test, or if you want to get certain tide states, you actually end up going out on the water at weird times of the night or the morning. And this is just one of my favorite pictures from doing an overnight test on the Energy Tide 2 in Cobscook Bay on a nice summer day. So all of that precursor test work is about developing the technology, understanding the technology. The next stage is to actually build it up into a product, into something that can be installed as part of a project. And that's the real focus of ORPC in the last 3 years, was to develop our TideGen project, our TideGen power system, and install it in Cobscook Bay. This is we'll go through that. To get to that point, we really had to step up our game in CFD modeling, as I said. We were a lot more sophisticated in our modeling tools. We're a lot more sophisticated in understanding the site conditions. Before, we were talking about doing testing off a barge. You could just throw out a mooring and moor the unit there. Now we actually got to stick this thing to the bottom and hopefully have it stay there. And there have been some high-profile failures of people who put their units down and they fell over, or they punched through the sea floor, or they got their location off by 50 meters and the flow speeds were different than they had designed for and the blades fell apart. So site characterization is really critical. We don't know enough yet to, there's still a lot of work each and every time you put a unit down and decide where it goes. So as an example of some of the work, we did some geophysical bathymetry work. You're looking for the depths, you're looking for the type of bottom, you're doing some ground penetrating sonar to look for bedrock underneath. You're mapping out all kinds of things. To confirm that, you actually have to go out and do geotechnical drilling. You've got to go get soil samples from different areas. And doing geotechnical drilling from a rig that's moored in 100 feet of water with a drill casing that's going down 100 feet, it's about that much around at 3 meters per second. Suddenly you find some vortex shedding events that are pretty impressive. So we have images of the drill casing swinging sideways about a foot. In addition to all the site preparation work, there's all the things that, this is actually a real power project that you've got to develop. You've got to do, believe it or not, you might have to do an electrical line upgrade. And unfortunately, you might have to pay for it because the local utility is not going to do it. And then the thing that the local utility forgot to tell us was that we were responsible for the internet line upgrades as well. So if you cut your internet, you hear about that pretty quickly from the locals. We had to install a subsea transmission cable, which turned out to be one of the technically very challenging aspects of the project. You'd think laying a cable would be pretty easy. And it would be, except that there are 5-knot flows over the site. So you've got to lay that cable in a very short window. You've got to get it buried in a very short window. If you leave it on the surface, you're just going to have that cable moving back and forth across the surface. And you've got to install a shore station to connect to the grid. So there's a lot of project work that needs to get done. It's not the big, sexy technical stuff. It's all the minor stuff. And then really, at the end of the day, it's the minor stuff that actually really matters. The other thing that we focused a lot of our effort on was how do you install and retrieve these units? We know we've got to put them in. We know we're going to have to take them out. And at the beginning of our project, we basically did all of our operations from a barge and crane. The barge was moored out in the water, and we had a heavy lift crane picking things up and down. That was a very high capital cost and was adding a lot of cost to the project. So we worked to develop basically a modular system that could be built locally on site using locally available pin barges and a winching system that can lift the TGU up and down, the tidal generation unit up and down. One of the things that we tried to do all the way through the project was to size all the lifting and handling equipment and all the on-water assets so that they're relatively commonly available in Eastport small communities. It's a different world in the North Sea or in the Pentland Firth where you have all the North Sea oil assets available to you. You have dynamic positioning drill rigs. You have all kinds of assets there. Maine is the same distance from the North Sea oil fields as it is from the Gulf of Mexico oil fields. So if you want to get a drill rig from the Gulf of Mexico, for a drilling operation to get some geotechnical samples, the quotes were ranging in the order of $3 million. In the big picture, what we've actually done is we've been permitted by the Federal Energy Regulatory Commission. We've got a pilot license, which allows us to connect to the grid, sell power to the grid. It was the first tidal power project to be approved for construction in the United States. We got the permit for construction and started installing the next day. So basically, we were waiting for that piece of paper from DC. We've got a power purchase agreement with the Maine Public Utilities Commission to sell power back to the grid at approximately 22 cents a kilowatt hour. In addition to that, there are renewable energy credits that are worth 3 or 4 cents a kilowatt hour. So that's a significant increment over the normal energy price in Maine, which runs about 5.5 to 6 cents a kilowatt hour. This project is the first hydrokinetic ocean project to deliver energy to any utility grid in the Americas. So ORPC has gone from a pretty small company in 2005 and 6 doing testing with wooden blades that were handmade in Eastport to being a world leader and to being the leader in the United States, and if not in Canada. It's a pretty impressive roller coaster we've been on. We're still going up. Some pictures of the project installation, turbines on the top left, the turbine generator unit on the top right, installing the bottom support frame for the first time over here, installing the TGU for the first time over here. That video that I showed looping earlier on had a lot of the installation sort of time lapses. And we can take a look at that maybe if we have time. Okay, so that's a lot of technology stuff is being developed. Some of it's new, some of it's just basic applied engineering. Like basic applied engineering, it helps to get the details right and to do your work well. As I said, some of it's new. The CFD modeling stuff is cutting edge. And some of the electrical design work is cutting edge. But all of that comes together and you have this wonderful project, or this product, but you can't do anything with it unless you can bring it to the market, unless you can install it and operate it. To install and operate a system like this in the United States requires that we go through a federal and state licensing process. And the federal licensing process is the Federal Energy Regulatory Commission's licensing process for hydrokinetic projects, which is based off the same process that's used to construct and permit and operate the Grand Coulee Dam. So if you take something that has the potential to the size of the Hoover Dam and the Grand Coulee Dam, that same process needs to be gone through for our little 150 kilowatt generator. And I noticed today that the power usage for this building is something in the order of 400 kilowatts on an average basis. So we're talking about 3 of these things to run this building. So we've got to do an extensive agency consultation process and feedback process, listening to a lot of people, getting feedback from a lot of different agencies. And that's at the state level. That's at the federal level. And the federal agencies involved, that's sort of a snapshot of all our federal agencies and the processes. We've got the National Environmental Protection Act, the Marine Mammal Protection Act, things I can't even read, water quality things, all the way across. The FERC process is set up because, in a way, we as a society have asked for these environmental protections to be placed on developing projects in the United States. There was a period in time when anybody could do whatever they want, and there was no consequences. And we didn't like the results, so we put in place a permitting regime that made everybody slow down, talk to people, consider the effects on the environment, get all that information together, and then make a decision. FERC's mandate is to give equal consideration to power and to environmental uses. And that's a balancing act that they have to make. So does it make sense to dam a river and create power from it, or is it better to leave it open as a canoe waterway? That's their decision to make, and it's not an easy decision. These projects have to serve the best public interest, and that's a high barrier to get through. It's also sort of, FERC acts as a clearinghouse. They actually don't do much of the work. They sit in Washington and ask other people to provide their comments. So it's a distributed decision-making process. And some of the federal agencies that are involved are things like the U.S. Fish and Wildlife Service. The U.S. Fish and Wildlife Service has a statutory mandate to protect endangered species in the United States. I want to use those words again, statutory mandate. You told them this is the law, they have to do it. So if there's a salmon run in Eastport, which there is, it comes under the jurisdiction of the U.S. Fish and Wildlife Service. NOAA, the National Oceanographic and Atmospheric Agency, has the distinction of being the single federal agency that is sued the most often. And the reason is that they're the ones who get to make these rulings on environmental projects, on environmental effects. Their mandates are under the essential fish habitat laws of the United States, which basically map out huge areas of the ocean that says that these habitats are essential to fish stock. And that's an extremely important industry for the United States, and it's important that we conserve and protect it. The Marine Mammal Protection Act. Okay, things with big eyes. Humans like things with big eyes, so we like marine mammals. I'm a little facetious about that. There are endangered species. There are about 350 North Atlantic right whales left in the North Atlantic. In Puget Sound, there are something like 86 orca in that particular pod that are genetically different enough from other orca. In Cook Inlet, there are 350 belugas that are a specific genetic population. All of those populations of marine mammals are critically endangered, and it's a serious problem. And one of the things that we have done in the oceans is make these oceans very, very noisy. We have a lot of ship traffic, a lot of sonar activity, oil and gas exploration, and now we're talking about building these renewable energy projects out to sea. So the marine mammal protection is important, but the interesting thing about our laws is that the North Atlantic right whale gets as much protection as a gray seal, which is almost a nuisance species in the coast of Maine. So there are harbor seals and gray seals, well, more harbor seals than gray seals, but lots of harbor seals. But to touch, harass, or do anything to annoy these creatures is actually against federal law. The Endangered Species Act, again, under NOAA. Then you've got people who are actually charged with managing navigation in U.S. waters. And, the Coast Guard does like to know that you can drive a boat over a section of water. And the Army Corps of Engineers gets tasked with saying, yes, you can build a structure here or put a mooring there. That's 4 agencies, and I think there's probably another 6 or 7 agencies on the federal level that have input. And then you get to the state level, and being a federal government, each state has a different process, and they're not necessarily aligned with the federal processes. In general, the state of Maine and the federal government work very well together. They have a memorandum of understanding that works really well. But my favorite state regulatory thing is the State Historic Preservation Commission. Anybody want to tell me why they might have an interest in a project offshore? I heard whispers. Sunken ships, archaeological finds and wrecks, and 10,000 years ago, this was actually dry land. So this was habitat for Aboriginal people. So the other stakeholders are those are all the legal and state ones, and those are important. We've got to take good care of those. But the ones that are really important are actually the local community where you're trying to build this thing. And in these communities, the most important stakeholder is the fishermen, fishing community. So we spent a lot of time doing outreach activities, talking to people, getting their feedback. I'll talk about it a little bit more later. But we've invested a lot of our energy in building public support at the local level for these projects. And then the other stakeholder that I keep forgetting about are the investors, or the guys who have to come up with the money. Our major investors are the Department of Energy, from which we've probably raised about $22 million over the last 5 years, and private investors for another $15 million. So we're very heavily funded by the U.S. taxpayer. Thank you. I appreciate it. But they have their own agent, they have their own audiences that they need to report back to, and it's always very important to keep those people in mind and what they need to do. So as I said before, we've asked for these protections to be put in place, and as a society, we want these protections. But how do you balance that against the desire to create what we consider to be a new, novel, and good technology? I'm generating electricity with renewable energy. I'm not releasing carbon. I'm not using fossil fuels. It's a good thing. I should be allowed to do it, right? But a lot of people in the past have said, I want to do it because I believe I'm right, and things didn't turn out quite so well in the end. So we've created this balance. We've created this regulatory process. It's slow, it's cumbersome, it can be improved, it should be improved, but there's always going to be this element of we need to do this in a very thoughtful manner. And there's no point, and I guess my message to you today is as you get into technology development, you know all about the technology development, you know all about the problems of technology development, you're out of time, you're out of money, it doesn't work, breaks, all that stuff. You know that stuff, that you expect that. But as you go to bring products to market, there's a whole other range of things that you need to consider and have to deal with. You can't ignore them. You actually have to embrace them and go out there and figure out how to work that system, whatever it is. And the best way to do that really is those old sort of things that your father or your mother probably told you, which is if you're honest with people, they tend to trust you more. So if you go out and you tell a consistent story to people and you're open with them and you're willing to listen to them, if you're willing to listen to a fisherman over a cup of coffee at 5 o'clock in the morning, if you show up at 5 o'clock in the morning to meet with someone, it means something. You can't do that from a cubicle or an office in Boston and do a project up in Eastport. It just doesn't work. You have to listen to people. You have to understand what the issues are, what they perceive the issues to be. And then you get into this process of these perceived issues. Are they real? And this is where your training as engineers and technology people really starts to come into play, because you have the tools to assess whether those are real problems. If they are real problems, you should address them. If they are real problems, you should figure out a scientific way to assess the problem, monitor it, maybe mitigate it. If they're not real problems, it's actually your duty to tell people that, this is not a real problem and this is why, and have that conversation. Too many times we have these lingering environmental concerns that have been around for 20 or 30 years that just haven't been put to rest because people like us aren't willing to stand up and say, hey, this is not a problem. Only by doing that, by engaging with people, by having those conversations, sometimes difficult conversations, can you really start moving complex projects through to completion. I want to talk a little bit about that debate about whether things are real or perceived to be real. At the federal level, at the regulatory level, they use something called the best available science. So basically, the federal agencies are supposed to make their decisions on the best available science. So technically, they're not supposed to be able to ask you to go out and do a 3-year study of something to figure out if it's a problem. They're supposed to use existing science. But the reality is that they generally ask you to go out and do a 3-year study to find out how fish are going to interact with the turbine. I mean, that's okay. That's a question that I think needs to be answered. How do fish actually move around this turbine? That's something that our other stakeholders, the fishermen, want to know, and I'm willing to invest the time in doing it to do that. One of my personal thing that aggravates me a little bit is conversations about EMF from subsea cables. Some people here may disagree with me, but we can talk about it later. We have laid subsea cables since 1850 something. I don't know, a very long time, over 100 years of subsea cables. And in all the studies that we've done to date, there have been very little effects noted on sea species. Some creatures may have some magnetic sensitivity, but the results that keep coming back in the studies are that it's within the realm of error of the study. Yet we continue to keep on asking people to do EMF studies on subsea cables. So, my attitude is, look, here's the scientific literature that proves that this is not a problem. Let's not do that. Let's not waste our effort on that problem. Let's use our energy and time on something that actually will provide us some new information. As you're having that conversation, it's important to realize that, again, as engineers, you're sort of in a unique position because you have that little bit of mentality in you that says, well, is this issue real? Well, yeah, okay, it's real. I'll do something about it. But if you can't measure it, there's no point in doing anything about it. Until you can come up with a test that actually discriminates a result, what's the point? And if you don't have any means of collecting the data that's valid and defendable, there's no point in collecting the data. So you shouldn't go out and just collect data just because you said you wanted to collect data. You should have a purpose and a meaning and a rationale. And you need to be able to stand up and say, look, I'll do this test. I could do this test, but it's not going to give me a meaningful result, so I'm not going to do the test. That process is the way we've worked it is through an adaptive management model. I love these new these terms that keep on coming round every 5 or 10 years. This is the latest one, adaptive management. And essentially it means that you just, as problems come up, you assess the data and you change your planning and your testing regime to address the new situation. So instead of saying at the beginning of the process, I will do the test plan like this for the next 5 years, you actually stop every 6 months during those 5-year periods and assess whether you're doing it right, and if not, you change it. It all sounds very sensible, but it's sort of new to regulatory agencies. So a little bit about the study plans that we actually do and the ones that I agree are necessary and valuable. The first one is the Benthic and biofouling study. And the benthos is this interaction zone between the sea and the sea floor, so the muddy layer that's the organic layer that's on the sea floor, in which all the shellfish grow, invertebrates grow. And it's a delicate area. It's sort of it's an economic source of fisheries in Eastport because 2 of the main fisheries are shellfish based. One is urchin, and the other is scallops. Those are dragging fisheries, so the benthic environment is very important. Biofouling on the structure is something that we need to look at because the growth of mussels and other kinds of biofouling materials on structures in the subsea environment increases the drag on the structure, so it increases the load on the structure. And there's also some chemical interactions between some of the adhesives that these creatures can generate and the paint systems that we have. Acoustics, we talked about a little bit about how loud the world's oceans are now. And so acoustics are a very important study area for us. We want to monitor how these individual turbines behave and how they would behave as a field as you build them out. As I said, fisheries interactions. Do fish go through the turbine? Do fish go over or around the turbine? Do fish get chopped in half by the turbine? The interesting thing is that in a tidal environment with fish swimming around, it's actually it's a very stressful environment for them anyway, because if they want to move upstream, they have to fight against the tide, just like you swimming, and it's tiring. So they would rather find a nice place to hang out for a while behind a turbine where there's no flow. So there's pictures of an open hydro turbine in the Orkneys at the European Marine Energy Center, where there are basically schools of fish just hanging out on the wake. It's a low energy situation for them. When you think about it, fish and mammals are not stupid, and they don't run into things. They don't run into walls. They don't run into rocks. They're very sensitive sensory perception. They have lateral, they're pressure sensing lines on their bodies. They can feel the pressure disturbances of these devices and run around them. So one of the studies that was required of a different competitor was that we do a flume test where you have a turbine in a tank, and you've got a water tunnel, and let's dump fish into it and watch the fish go through the tunnel, or go through the turbine. So the first thing the fish did was they got dumped in one end of the tank, and the water was flowing away, and they swam as fast as they could over into the corner away from the turbine. So the only way they could get the fish through the turbine was to actually put nets around the turbine, put the fish inside the net, and then kind of push the net through the turbine. At which point all the fish got through the turbine just fine. They didn't like it, but it got through there just fine. Just a sidebar on the conventional hydro projects, fish passage is critically important. There's a barrage dam, a tidal dam, just a normal dam in Annapolis Royal in Nova Scotia, which is a tidal barrage dam, empties in and out 4 times a day. On each passage of that, the fish mortality rate is 80%. So that's just a mincer. And the reason is that in conventional hydro design, the energy is extracted from the water by rapid depressurization of the fluid. And a lot of fish have an internal swim bladder that you just basically decompress the fish very quickly. So environmentally friendly hydro turbines are now moving towards a lower decompression rate as you move through the turbine, and that works really well. And our systems, they're really harvesting the kinetic energy, so there's not that much pressure change through the system. Sea and shoreboard monitoring. I didn't know that birds could dive to a depth of 80 feet before this project, but they can. And then hydraulic monitoring. We want to know if we're changing the tides in the rest of the area. So basically, we got a resonant system here. You know, what happens if you start damping it locally? Do you create some other big effect someplace else? So we do monitoring by measurements of flows in different places and also by circulation modeling. We also do some marine mammal observations, which I'll talk about in a minute. As we're developing these new technologies, and people are asking us to do things in environments where it's not commonly done, you don't moor a boat in a 5-knot current. It's not the point of a mooring. You avoid the fast flow spaces. It's been really hard to collect data in areas with high flows. So we've been developing lots of different techniques and solutions for collecting environmental data, including acoustics and fisheries interactions. This is an example of some work done by the University of Maine, basically using commercial fisheries equipment, fish finders for commercial trawlers, and just mapping out fish signals over the turbine. So some of those blue dots represent fish. The red structure represents the turbine. And you can see there's some aggregation of fish in various places, but no observed mortality from their results. Mammals are a good one, and this is sort of our catch-22 of our permitting process again. The best way to see things underwater is with sonar, and as I just said, noise really annoys the mammals, so the agencies are asking us to go look for the mammals. So what do? We put a sonar in the water, but you need a permit to operate the sonar. So you can only operate the sonar like 2 hours a day, 12 times a month. We try to protect things, and sometimes we create more problems for ourselves than we want. So right now, I mean, in terms of our project, in terms of our studies, and in terms of the impacts, we have a renewable energy technology. It's created significant amount of economic development locally. We use a lot of the waterfront facilities. We use a lot of the local workforce and skill set to install and operate these units. And to date, we have non-observable, no environmental effects, negative environmental effects created to date. No strikes of fish or marine mammals, not just in our project, but in every single hydrokinetic project in the world. There has not been a recorded incidence of a fish mortality or marine mammal that I am aware of. And there's no indication of deterrent effects or barrier effects. And the question that we have to ask ourselves moving forward is we do a lot of monitoring. It's very intensive. What's the appropriate amount of monitoring as you build out a project and make it bigger? And that's part of the negotiation and the conversation that has to happen as we move forward. So I think, as I said before, to summarize, the thing that I'd like you guys to maybe take away from this, other than this is cool, and maybe you can do it too, is that you understand technology development, you're used to it, and every day you go to the lab and you fight those problems. But as you move things out into the real world, some things just crop up that you've never even thought about. And you don't have to be scared about it. It just is what it is. You just got to deal with it. But go out and deal with it in a way that's open and honest and inquisitive, and people will respect you and engage you and probably help you along. If you can carry these people along, you're almost guaranteed your project will succeed as long as you can get the technology to work, which is still important. Never forget the technology at the end of the day, because you still have to get that to work. And with that, I want to say thank you for your time, and I'm open to any questions you all might have. That's a bad thing. So the design life for the structure depends on the different structures. So which is left in there, it's a 25-year design life. The framework on the TGU chassis is a 15-year design life. The turbines are 15 years design life. The bearings need to be replaced every 5 years, so that needs to come up every 5 years. If something breaks, depends what it is that breaks. It's got to be bad enough that you actually have to take the unit out. If you can operate with a broken bolt, we operate with a broken bolt. But if you break a blade off and the whole turbine goes out of balance, you've got to take it out. Yes, sir.
So you're also clearing off any biofouling every 5 years?
Yes, the biofouling question is interesting because the blades themselves appear to be self-cleaning so far. So basically there's enough water flow and enough motion there to clean the blades. The areas that are open to the flow appear to be very clean too. But areas where we've designed, just unintentionally kind of dead-end zones, they are definitely fouling, and you could argue that they're not critical, so just leave it. The areas which are really biofouling rapidly are areas where it's warm. So on a generator surface or a power electronic surface or a connector, where you're getting heat buildup in addition to that protected flow, you're accelerating the growth. And that we do need to deal with. But we went into this project actually not using biofouling paints because no one could guarantee that, well, you have to replace paints every 3 years, and that wasn't consistent with our view. So we decided to try it and see what happened.
Jarlath, I had a question. You showed concern for fishes and mammals, but what about if there are divers in the area? Do you have provisions for that?
So the part of the Coast Guard's mandate is to mark the charts, and the charts are labeled as tidal turbine zones and no dredging or diving.
Well, I'm glad to see you guys have thought about that. Are there any other questions?
In your geomap, when you're actually doing soil concentration or soil type, you mentioned that if you place a system at like different locations that you can get very different energy rates, can you actually make a field that would be coherent or organized?
Yeah, this is a relatively small geographic area, and it has very localized flow patterns. So the area that's circled up there is actually our site area that we're installing. We can install 5 units in that section, I think, without any interference between the adjacent units. But that question is an active area of research. How closely can you pack these together? And if you install one, what the effect is on the subsequent units. The technique for addressing that question right now is by modeling. Yes, sir.
I have 2 questions. One is about the whales. Presumably just like a couple units here and there, prototypes are not a big problem for noise, but as you keep, if the hope is to produce power for some fraction of the U.S. need, that's an awful lot of units. Is there some, I don't know, it must be preliminary work on trying to figure out how the noise level goes up and how far the noise
Yes.
travels?
Yeah. So again, we do acoustic models and acoustic measurements off this unit and correlate the models, and then build out models of how a field goes. And one of the appropriate questions going forward is, are the noise effects additive? Having said that, one of our competitors is building a project in Puget Sound in Seattle, and as I said, there's an orca population there, and already the noise levels in that body of water are above harassment level for mammals, primarily due to ferry traffic. So, there are areas that are already potentially overdeveloped.
Is the thought once it's too loud, then it's okay to add more because it's not going to affect the area?
No, that would be breaking the law.
So the other question was a more technical one. Trying to attach it to the seabed.
Yeah.
I'm just guessing that that's probably a very expensive part of the whole operation.
You are correct.
What's best? On the map here you have, exposed ledge.
Yeah.
That would be very difficult to get into, but
Yeah.
very stable thing. And gravel, and what's sort of your preferred approach?
We don't, we're developing a preferred approach, but this project actually we drove piles into sediment, and it was actually relatively easy. We'd never done it before. We were really kind of worried about how it would go. It went very well. We're developing mooring systems for rockier bottoms, and we're working with partners who are developing subsea rock anchor technology, so subsea rock anchor drills that insert a it in place into ledge bottom. But that's a pretty active area of research. Yes, sir.
I was wondering what the highest efficiency that one of these is.
Okay. Practically, a wind turbine today gets in the order of, I think, 46, 47% extraction efficiency. The cross-flow turbine, I think, inherently is going to be a less efficient design. I like it because of the low profile that it has. It fits in river systems better. It's more water clearance. But I think we'll see in the high 30s from that design. The real question, actually, it's sort of a good question, but a wrong question. The real question is, what's the dollar cost per kilowatt hour? If you can invent a system that's really cheap but very inefficient, it might be a better system.
I invite anyone interested in discussing any further questions with Jarlath, and we'll bring this to a conclusion. Thank you, Jarlath.
Thank you very much.